You got it? All right, I'll begin. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray you guide our steps today. Help us to, again, Lord, just to glorify you, Lord, what we do, Lord. In your name I pray. Amen. All right, so today, I'm going to talk to you about the technique of partial fractions, or as it's sometimes called, partial fractal decomposition. All right, so that's what I'm going to talk about today. But I guess before I start talking about that, I'll ask you if you have any questions about anything in particular before I get carried away with another action-packed episode of Calculus 2. Did I not post the, if you look at the solutions I've posted, the problems that I mentioned are in the solutions, so you can see them there. There's like 4. You're talking about the hyperbolic problems, right? Mm-hmm. So look at the solutions that are posted, cover up the solution, write down the problem, and then try to do them, you know. So other questions? That's a very, very good question. If you email me, I can post the blank ones. I just forgot to. I got it somewhere. All right, so I'm going to talk about this. We should have, again, we have time for homework questions tomorrow. If you have more tomorrow, it's cool. So the quiz next Monday is on trig substitution, hyperbolic substitution, and partial fractions. Right? So I want to start talking about it today so you have a chance, hopefully, to think about it some more after class and ask questions about it tomorrow still. Right? Yep.
The quizzes are they always on the stuff that you learned the week previously?
Yeah.
Just the week previously?
Well, this is Calculus 2, so it always builds on it. I mean, I can never quite make that promise, but it will tend to focus on the week before. And anything I've complained about in the quiz before, possibly, like if I'm like, you guys should get this, why did everybody get this wrong, blah, 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 then the likelihood that I ask a question on the following quiz to see if people fixed it exists. But, you know, I think trig substitution, hyperbolic substitution, and partial fractions is plenty of trouble for one day. But I don't know. I mean, the stuff we did the previous quiz could still appear. It's just not the emphasis, right? You want to learn that stuff pretty soon because we have a test, you know, not too long anyway. But okay, so partial fractions. Why do we need partial fraction? What's the story? And so let me start with the story of basic rational functions. So what are the basic rational functions? There are really basically 2 kinds. The one is something like 1 over x minus a to some power n, right? That's the one kind of basic rational function you got. The other kind of basic rational function you got is something like this. Let's see here. Oh, I don't know. Something like 1 over x minus alpha squared plus beta squared. But it could be that, or it could be like c1 plus c2 times x minus alpha. So I guess I could. I mean, there's sort of just 2 different things that happen here, right? I mean, the one is something like 1 over x minus alpha quantity squared plus beta squared. The other is something like x minus alpha over x minus alpha quantity squared plus beta squared. So, I mean, you could break it up into, I mean, I was just saying, C1 and C2 are constants, so maybe I should think of it as this and that. Maybe that's better. But I'm still not done. I mean, this also, you can take the denominator and you can raise it to any power n. these three things, all right, for just different choices of n. So there's not really three things. There's lots and lots of things. But these three basic types suffice. I mean, you can break basically any rational function into a sum of these three sorts of things. So that's the technique of partial fractions. But before I get to that, let me just remind you how we can integrate these things. So for example, if I have integral of dx over x minus a, how do I integrate that? Just let u equals x minus a, right? But if I have the integral of dx over x minus a to the n power, so suppose n is greater than 1. This was n equals to 1, right? Which is special. Again, make the same u substitution, right? And we get what? I'm an idiot. That's supposed to be a du, right? Sorry. Yeah. So you do minus n plus 1, right? Divided by minus n plus 1 plus a constant. In other words, we have, I mean, this can be written in various different ways, but here's one way you can write it. X minus a to the 1 minus n divided by 1 minus n plus a constant, right? The point is, we know how to integrate that. We know how to integrate this. In fact, we can integrate any power of x minus a to the n, right? None of those can escape. We kill them all, right? Oh, I'm sorry. I seem to be getting violent again. How about these guys? How would you do these integrals? Here, alpha and beta are constants. Let's start out with a basic case. How would you integrate? I'll start with the x minus alpha. X minus alpha dx over x minus alpha quantity squared plus beta squared. How would you do this integral? What if we make the whole denominator, say, u? What do we have? Upstairs, we have 1/2 du divided by u. So we get 1/2 log of the absolute value of u plus a constant, or if you like, the natural log of the square root of x minus alpha quantity squared plus beta squared plus a constant. So we can do that kind of integral, right? How about without the x minus alpha upstairs? Then what are we dealing with? How about this guy? How would you guys suggest I do this integral? In the spirit of this week, we should think about a what substitution? Yeah, trig substitution. I suggest we make x minus alpha equals to beta tangent theta. All right, then this is going to be the integral of beta secant squared theta d theta. And downstairs, I've got what? I've got beta squared tangent squared theta plus beta squared, otherwise known as beta squared secant squared theta. Oh, the secant squared canceled. We're left with 1 over quantity beta, integral of d theta, or if you like, theta over beta plus a constant, otherwise known as 1 over beta, inverse tangent of x minus alpha over beta plus a constant. We could have done that before trigonometric substitution. In fact, we did. Remember, we factored out the beta. We made it look like 1 plus something squared. We made a plain old u substitution. We did a problem like this early on, before we got to trig substitution. So you're like, okay, well then what's left in this litany of how to integrate basic rational functions? You got to worry about n greater than 1, right? So for n greater than 1, first of all, if we have the integral of x minus alpha dx over x minus alpha squared plus beta squared quantity to the n, what do? Same thing we did last time, right? Just let, yes, sir? N greater than 1, what? Well, but there's different cases. All right, so like this guy, this one, and that one. In contrast, these two guys, this case, and then that case. I can either have a repeated linear factor or I can have a repeated quadratic factor. Right now I'm talking about the repeated quadratic factor. Forgive me, this part's a little bit boring, but we have to get through it just for the sake of logical completeness. So this is what? This is, we'll let this thing be u again, right? And so again, u substitution, I have 1/2 du upstairs. I've got u to the n downstairs. So I get, that's u to the minus n, right? So I get 1 over 2 times 1 minus n, 1 over u to the what? N minus 1, right? Plus a constant. Of course, you could write this, if you like, you could write it 1 minus n over 2 times 1 minus n plus a constant if you prefer that, whatever. I'm going to stick with this form. So that gives me 1 over 2 times 1 minus n, and then 1 over what? Over x minus alpha quantity squared plus beta squared to the n minus 1 power. What's left? One more case, right? Of the form, this guy, dx over x minus alpha squared plus beta squared to the n power, and n is greater than 1 here, right? So what can we do? Pretty much the same thing we did in the last case. We can make a beta x minus alpha equals beta tangent theta substitution, right? And if we do that, what happens? If I make that substitution, I get what? I get myself beta secant squared theta d theta in the numerator, right? But downstairs, what do you get? You get you get beta squared secant squared theta to the what? To the n power. So to clean this up just a little bit, this is 1 over beta to the 2n minus 1, the integral of, let's see here, what's this? We got secant squared theta, let me just clean it up down here. Secant squared theta over secant to the 2n theta, right? Which is what? Secant to the 2n minus 2 theta, right? AKA cosine to the 2n minus 2 theta d theta. Can you integrate an even power of cosine? Do you know how to integrate cosine squared, for example? If we put n equals to 2, we get 4 minus 2, which is 2. So that when we have a square downstairs, we get integral of cosine squared there. Can you do that integral? You can integrate cosine squared. You can do it. Believe in yourself. Can you integrate cosine to the fourth? Yes. You see, I'm asking you if you can do it. I'm not asking if you want to do it. You're confusing my question. You can do it. You don't want to do it, right? The point is, those we can do. I'm not going to try to write the formula generally speaking, but there's really nothing stopping us from integrating anything of this form, because we can make this trig substitution, and it's just a matter of work, right? We can find a formula. But obviously, things of this form are a little bit nastier than anything else we looked at here. All right? So here's the theorem. Any rational function. What's a rational function, guys? It's a quotient of two polynomials, right? So any rational function can be written, or rewritten if you like, as a polynomial plus a sum. Well, let me be more descriptive. As a polynomial plus a linear combination of basic rational functions. What's the linear combination mean? What this means is you add things together, all right? But you're also allowed to multiply those things by numbers as you make the addition. So. So let's see, let's look at some examples. So, for example, if I have 1 over x squared minus 2x minus 3, all right? My claim, if you believe the theorem, which I'm not going to prove this theorem, I'm going to give you many examples of how it works, right? So here's the way it works. You factor what you got down here. This is what? X, I hear x plus 1, x minus 3. Does that work? Let's see, we get minus 3, we get a plus x, a minus 3x. That gives us a total of minus 2x. It's legit, right? Now this, here's the partial fractions. We say that that's a over x plus 1 plus b over x minus 3. So basically what we're going to see again and again and again and again and again is however the denominator factors, that will inform you as to the kind of basic rational functions you need to form the fraction. Right? So like here, I got an x plus 1 and x minus 3. That told me I should look for a linear combination of 1 over x plus 1 and 1 over x minus 3. So, okay. And past that, it's just algebra. So multiply both sides by the denominator. And that gives me what? 1 is equal to, I'm going to write this just once, so guys, watch it. I don't usually write down this step because it doesn't need to be written. You should do it mentally. So, what happens? Right, the x plus 1's cancel. We get what? A times x minus 3 plus b times x plus 1, right? How do we figure out what a and b are? They're basically two strategies, but here's a nice one. For this one, they're distinct roots. A nice thing to do is just plug in values. So you might worry that plugging in values doesn't make sense because that's where we have division by 0 in the original expression. But for reasons I won't go into, it's fine. Now, if you don't believe me, you could always just check my answer. I'll show you how to do that in a second. So x equals to 3 gives us what? Plug in 3 here, 0. This is what? 3 plus 1, 4b. If I plug in x equals minus 1, this goes to 0, right? And this goes to minus 4. So I get 1 equals to minus 4a. These equations are pretty easy to solve. Agree? So this gives us what? b equals to 1/4, and a equals to minus 1/4. And lo and behold, we found our first partial fractions decomposition. 1 over x squared minus 2x minus 3, right, is equal to, apparently, minus 1/4 divided by x plus 1 plus 1/4 over x minus 3. Now, I personally, I mean, that's it, right? But you could clean this up a little bit. This is what? This is really 1/4 of what? Right? So that's kind of a nice way to just to clean it up a little bit. Why are we doing this? Well, our main mission in here at the moment is to solve integrals, right? And to learn algebra on the way of doing that. Lots of algebra. And you see now this, this algebra we just did allows us to integrate that, right? If you try to integrate 1 over x squared minus 2x plus 3, or minus 3 rather, well, that's not something you can do straight up, right? I mean, I guess I could complete the square and use an inverse hyperbolic tangent after a u substitution, but you guys don't want to do that, am I right? Because then you got to worry, are you right in the right domain? Because you might need to use an inverse hyperbolic cotangent, depending on where your x's are. You'd have to break into cases. So we don't want to do that. So instead, we use partial fractions, and then we just face these innocuous little integrals, right? Can anybody tell me how I could rewrite the answer as a single logarithm? Right, so yeah, we could rewrite this as the natural log of the absolute value of x minus 3 over x plus 1. And I could bring the 1/4 inside even if I wanted to the 1/4 power plus a constant. So you could write it that way if you wanted. But, you know, the main point here is the partial fractions decomposition. That extra bit I did at the end was just for kicks. All right. So, I said something about checking my answer. How do you check your answer here? I mean, what is partial fractions? Let me do something a little bit different. How about 1/3 plus 1/7? What do you got? You got 7 times 3, right? Plus 3. Oh, I mean, excuse me, let me say 2/3, make it more exciting. So 7 times 2, right? Plus 3 times 1 over 3 times 7, right? Which is what? 17 over 21, right? What we're doing here is the same thing, except it's kind of weird, right? Like, nobody usually tells you, hey, take the fraction 17/21 and rewrite it as a sum of some number of thirds and some number of sevenths, right? But you can do that. That's called, well, my terminology, reverse common denominatoring. Reverse common denominatoring. I can't spell denominatoring. There, I took the time to spell it. Are you happy? Reverse common denominatoring. Right? You'd never think to do this with fractions because it would be silly unless you're a number theorist. Right? But that's exactly what our business is here. We're trying to take these and rewrite them as a sum of fractions because it can be done because of this theorem. It can always be done. You can always rewrite any rational function as a polynomial plus a sum of basic rational functions. And when you do that, why is that awesome? Because we can integrate any basic rational function. So once you do this algebra step, you can integrate. So that is partial fractions.
How does the, towards the end of your problem, how does the 1/4 from the outside of parentheses go to ln and all that stuff to 1/4?
Oh. Because the log of a, p log a is equal to the log of a to the p. Yeah, and p is equal to 1/4. So, another example. Suppose you wanted to integrate x squared over, I don't know. I'll start us out pretty simple, x minus 3. Oh, that's too simple, actually. Too simple. Let's say x squared plus 2 divided by x squared plus 4x plus 5. There, that's a problem with a little more meat to it. I'll tell you what, take that x squared and raise us an x cubed. There we go. Now it's sufficiently ugly. I feel better. So, I warned you guys, polynomial, right? I'm trying to remember, when did we stop in here at when? I was going to give you 50 minutes, so we started, when did we start? 3:45, so we stop at 4:35, right? Yeah, okay. So how are you guys going to, this polynomial, where's this coming from? What? How do you get a polynomial out of this? So the claim is it's polynomial, right? Plus some basic rational functions, right? Where's this polynomial coming from? Anybody know? Ah, yes, the long division. That is the idea. So you guys know long division, right? So I don't even need to talk about that. Right? Just kidding. I know I need to talk about it. So here we go. So what we do is we put ourselves, we're going to do what? X cubed plus 2 down here. And we're dividing by x squared plus 4x plus 5. You're like, but I like to do synthetic division. Well, that's too bad, because you're dividing by a quadratic. So synthetic division is useless. Sorry. I have a certain animosity towards synthetic division. Anyway, x, put x there, because that x gives me an x cubed. Take the difference of these things, we get 2 minus 4x squared minus 5x. Let's see here. Then I'm going to do what? Minus 4. So that gives me minus 4x squared minus 16x minus 20. The 4x squareds cancel, right? So I get 22. And plus 11x. Yeah. You can always check your work with Wolfram Alpha here. It doesn't take long to do it. Like if you say if you like type into Wolfram Alpha this partial fractions, it should produce what we're doing, so you can check yourself, right? Now, that's as far as you can go. That's the remainder, because at this point, that's smaller degree than that, so there's no way I can multiply this times some polynomial and get rid of that, right? So you put all this together, what does this say? This says that x cubed, here's how we interpret this calculation, x cubed plus 2 divided by x squared plus 4x plus 5, all right, is equal to x minus 4, all right, plus 22 plus 11x over x squared plus 4x plus 5. So there's the polynomial that we're looking for. So, so what we have then is we have the integral of x minus 4 dx plus the integral of 22 plus 11x divided by x squared plus 4x plus 5, right? Any questions about this part? So, I mean, the logic is just the same as long division with numbers, really, right? You just keep subtracting things and multiplying in this pattern. Can I erase? I mean, we're not done yet, but can I erase the, everybody? Oh, okay. I'll work over here. Yeah, go for it.
Why is it that we're splitting it up? Like, does that just make it simpler?
Well, we know how to integrate basic rational functions. So the starting point,
Oh, okay. So
I
it's more complex.
yeah, basic, I mean, the larger point here is that f of x is basically equal to p of x over q of x, right? But what that's equal to is I need another letter, I don't know, g of x, all right? Plus I need another letter, h of x, okay? Divided by q of x. It's the same q. So here, this right here is what I would call a proper rational function, in the sense that a proper rational function has the degree of h less than the degree of q. And those you can rewrite as sums of the basic rational functions, actually. But first we got to split off this polynomial piece because it's in the way. So really the first step of integrating a rational function is it proper? All right. If it's not proper, you do long division, split off a polynomial, and then you're left with a proper rational function that will do the partial fractions decomposition on. All right. So we split off the polynomial piece. You know how to integrate x minus 4, right? That's easy. But what about this piece? So I'll do it. I mean, I'll do this piece, right? That's 1/2 x squared minus 4x plus what? Here we have the integral of, let's see here. This is what? This is x plus 2 quantity squared, right? Plus 1. So what I should do is I should rewrite the numerator in a way that serves my purposes, right? So what do I want? I don't want x. Like, x is no good to me. I want x plus 2. So check this out. Here's a little trick. 11x is equal to 11 times x plus 2 minus 2. right? In other words, 11x is equal to 11 times x plus 2 minus 22. Cool. So that means, oh, that's weird. Oh, I'm an idiot. Yeah, I'm an idiot. So yeah, there's this thing called factoring. X plus 2 dx. Oh, cool. I just made this example. I mean, I'm sorry, I prepared this before class so that the integral would be easier than it might otherwise be. No, this is an accident. Generally, there should be 2 integrals here. This just happened to be the easy kind, too. It's the, we're like in this case. It's like this. So we can just make a u substitution, right? So you let u equal to x plus 2 squared plus 1. And so 1/2 x squared minus 4x plus 11 over 2, natural log the absolute value of x squared plus 2, x plus 2 quantity squared plus 1 plus a constant. Of course, I can clean this up if I want to. I guess I'll clean it up a little bit. Minus 4x plus, I'm going to leave the 11 outside, but that's the log of the square root. And I don't need the absolute values there. Why don't I need the absolute values? Right, it's the sum of squares, I heard. Did I hear that? I mean, this is the sum of squares, right? So it's positive. Smallest that thing ever is 1. It's never smaller than 1. And there you go. There's something different about these examples, right? What's the difference? Right? What difference does it make? As we look at the denominators, this denominator, right, versus this denominator. How are they different? Right, one has real zeros and the other one does not. One cannot be factored over the reals. It's an irreducible quadratic, right? If you look at its graph, if you look at the graph y equals x squared plus 4x plus 5, it never crosses the x-axis. This guy, on the other hand, the graph of just the denominator, hits the x-axis at minus 1 and 3, right? Can be factored, can't be factored, right? But we can complete the square, right? So, and that's important. Now let me let's take a swing at another example. First of all, let me address the thing I was doing that confused you guys. Let me come back to it again. If I have something like x squared dx, x dx, over x squared plus 6x plus 13, I think that one works nice. I should probably try to do a different one. Let me think about that. I think if I put a 16 here, it's interesting. Wait a minute, no, too small. 34. All right. So what is this? So this problem here doesn't really require the partial fractions technique. It's really just getting back into how do you actually do these kinds of integrals, right? So I complete the square, x plus 3 squared. To do that, I've done what? I've added 9. So I got to take 9 away from 34. That leaves me what? 25. All right. Yeah, 5 squared. So, all right, so here, then I'm going to do the trick. So I take x, I add 3, and I subtract 3. Why do I do that? I do that because then I have, on the one hand, this kind of integral, right, which is a u substitution, and I have, oh, fine, this guy over here, right, which is an inverse tangent. So, just getting to the point, this is the natural log of the square root of x squared plus 6x plus 34 minus 3 over 5, the inverse tangent of x plus 3 over 5 plus a constant. Where I'm using these guys, right? Notice that beta is equal to 5, and alpha is in fact equal to minus 3. Minus a minus 3, you know. So that was the trick I was trying to do. It's just, it's stupid when you can factor. The trick, the adding 0 trick to create an x plus, to create the sx plus 2 here, it's just unneeded when you can factor. So I'm an idiot. Sorry about that. I'm a victim of my example being too nice. I'll get over it, don't worry. All right, let's look at some more. So I just want to show you how we set up. And there's always some controversy here. Students don't want to believe me. But pretty much blah, all right, divided by x times x minus 1 squared times x squared plus, let's say 3. What would the partial fractions decomposition be for this? I say blah, but we have to know something about blah. Blah should be what? Can't be more than what order? It's got to be a polynomial for one thing, right? Blah is a polynomial. And it can't be more than order what? 3. 3 is okay. 4 is okay. 5 is where we get into trouble. Because this is a quadratic times a quadratic times a... This is a quintic downstairs, 5th order. Okay, so here's the partial fraction setup. It's a over x plus b over x minus 1 plus c over x minus 1 squared plus dx plus e over x squared plus 3. Before you ask me questions, let me show you another example. If I had x cubed times x squared, let me complete the square already. So like x plus 7 squared plus 64, and then times x minus 3. For example, yada can't be more than order 3, 5, 6. It has to be less than 6th order. Polynomial. But here we go. This would be a over x plus b over x squared plus c over x cubed. Then the most convenient thing to look for is d plus e times x plus 7 divided by x plus 7 squared plus 64, and then that guy gets me an f over x minus 3. Now, you could look for d plus ex, let me call these tildes because they're not the same constants then, over this. You could do that, but I would say, why do that? The whole point of finding the partial fractal decomposition is so that you can integrate, right? When you find integrals with an x plus 7 in the numerator, that allows you to make a u substitution on the e piece, and it's an inverse tangent on the d piece. If you just solve for d tilde plus ex, e tilde x, you've still got more algebra waiting for you after you do this algebra. So don't do it. So what's bothering you guys? Some of you, if I had to guess, don't want me to do this. You want me to do b plus cx over x minus 1 squared. Am I right? Don't feel that way yet? I mean, this is not the right pattern. It doesn't work. So let me see if I can explain that. Here, let me try to explain that. Let's see here. How can I convince you that this is not what to do? I feel like I have now probably made some of you do this by writing this, and I'm sorry for that. I know it's a vicious circle. I should really just not talk about errors students make. Then I would at least not be to blame. How about this? Why don't we try reverse common denominatoring to see what happens? So what happens if I take like 1 over x minus 1 plus 3 over x minus 1 squared? What happens when you make a common denominator of those? Yeah, I get x minus 1, right? Plus 3 over x minus 1 squared, right? Which is what? X plus 2 over x minus 1 squared. Oh, no. It is of this form, isn't it? So why don't we do that? Why do we not use this as the partial fractions decomposition? Was what? Right. It's not it's not nicely integrable. Integrable. Yeah. So if you write this instead of that, I will take off points. If I ask for the partial fractions decomposition, it is what I'm writing. These are examples of the partial fractions decomposition. Right. Let me see if I can show you guys another example here. If I had 3x squared plus 7x minus 2 divided by x plus 1 squared, x squared minus 1, let's say minus 16, times x minus 4 times x squared plus 1, what would I get? What would the setup be? I mean, you realize that this is just the first step, right? I would actually have to tell you what blah is or what yada is, and then you do algebra to figure out the A, B, C, D, E, F, G, H, I, J, K, whatever. So here, you best not do this before you do what? This right here is what? So it's dangerous to do partial fractions until you have a complete, like mastery of the factorization of the denominator. If you don't understand how to factor the denominator, you don't know how to do the partial fractions. So this is x plus 1 squared. You see, I've actually got 2 copies of x minus 4. Uh-oh. Well, I guess this is my last example. And then we've got x plus 4, right? And then what? X squared plus 1. Let me square that just to be unpleasant. All right, now do I have any common factors? I mean, I've grouped everything that goes together, right? And so now I can write down the partial fractions decomposition. This is a over x plus 1 plus b over x plus 1 squared. That takes care of this one. Then I've got from this pretty much the same thing, but with x minus 4. All right. And then what? Plus e over x plus 4. That takes care of this piece. And then for the last one, I've got myself an fx plus g over x squared plus 1 plus hx plus I over x squared plus 1 quantity squared. And that's all from this guy. On the test, I might ask you to set that up, but I wouldn't actually ask you to find A, B, C, D, E, F, G, H, I, most likely. Because I don't want to grade that, right? Before we go, what's the pattern? The denominator is quintic. 1, 2, 3, 4, 5. How many constants? 1, 2, 3, 4, 5. Okay, the denominator, 3, 5, 6. 1, 2, 3, 4, 5, 6. You can check whether or not what you're doing is right, at least partially, by making sure you have the right number of constants. This is 2, 4, 5, 9. If you remember the alphabet code, J is 10, so I is 9. We're done. Yeah. Thanks, guys. You can hit it. We're done. We'll do more of this tomorrow, and I'll take your questions.